It was the spring of 1967, and the Cold War was underway. The US was on high alert for attacks coming from the Soviet Union, and on May 23rd, the radio communications suddenly jammed. Did the USSR bug the system? Was this an act of war? A fleet of US Air Force bombers was poised to launch a counterattack, an act that might have sparked nuclear war. But just in time, vital information was relayed by an unlikely group. Weather forecasters? Hi, I'm Sage. This is Crash Course Geology. No, you didn't accidentally click on a Crash Course US history video. To understand what really happened during the Cold War, we've got to dig deep, all the way to the Earth's core, the hot, dense center of the planet. Last time, we learned about the Earth's top two layers, the tough crust and the taffy-like mantle. But for a long time, we could only imagine what was at the center of this big blue marble. Back in 1692, Edmund Halley was the first to describe Earth's core as something separate and disconnected from its shell. He described an internal structure known as the hollow Earth model, where a series of hollow spheres rotated around a central core. He argued that both Earth's shell and core had something called a magnetic field, each with two poles, or points of attraction and repulsion. Think of the magnets on your fridge. The same forces that draw a magnet to the fridge and push two magnets apart make up a magnetic field. But Halley wasn't quite right. He based his theory on Newton's calculations of the density of the Earth and the Moon, which were off. Look, Newton basically invented physics. It's okay for him to take an L once in a while. Hundreds of years later, scientists developed the field of seismology to study Earth's insides. Tracking seismic waves within the Earth helped British geologist Richard Oldham find the first evidence of Earth's core in 1906, and led British physicist Harold Jeffreys to suggest that the core might be liquid 20 years later. It took another decade to discover what was really at the heart of our home planet, thanks to one of my geology rock stars. Hit it, Dwayne. When Inga Lehmann was growing up in late 19th century Denmark, most people didn't expect much of girls, but that didn't hold her back. As a kid, Lehmann attended a progressive co-ed school in Copenhagen, but she didn't find the same egalitarian attitudes when she studied math at the University of Cambridge in England. Women could attend lectures, but they couldn't officially enroll, or use labs, or libraries. And while she eventually finished her math degree in Denmark, what she really was interested in was earthquakes. In the late 1920s and 30s, Lehmann filled index cards with information about earthquakes from all over the world, looking them over in her garden, storing them in empty oatmeal boxes for reference. While she was studying a large earthquake that had occurred off the coast of New Zealand, she noticed that some of its seismic waves had acted weird. They seemed to travel into the Earth's core before bouncing off of some kind of hard boundary. That didn't fit with the dominant idea of a gooey liquid core. So in 1936, Lehmann published a paper theorizing that the Earth's center consisted of two parts, a liquid outer core surrounding a solid inner core. Lehmann passed away in 1993 at the age of 104, living long enough to see her theory about the Earth's core become widely accepted scientific consensus. Lehmann solved one huge mystery, but there's still so much to learn about Earth's core. Further seismological research confirmed the makeup of that inner core, iron and nickel. But a 2025 study of seismic waves showed that the core may be changing shape and even changing the direction and speed of its rotation. There's also evidence that the inner core isn't completely solid, but sort of squishy. And there may even be another layer, creatively named the innermost inner core. Like, come on guys, Dwayne could do better than that. What? No shade, Dwayne. Okay, so the core of our planet is a hot ball of iron and nickel. But it isn't just like chilling there. That ball of metal basically functions as Earth's bodyguard, using invisible armor to protect us, a magnetic field. The hot metal in the core's molten outer layer is constantly in motion, creating currents that generate a magnetic field surrounding the Earth. That field has two poles, north and south. Not to be confused with the geographic north and south poles. No penguins or Santa Claus here. Like in any other magnet, the magnetic field moves in a continuous loop, entering Earth at the north magnetic pole and leaving from the south magnetic pole. In space, the influence of Earth's magnetic field extends tens of thousands of kilometers around the planet, creating a bubble known as the Earth's magnetosphere. The magnetosphere is constantly moving and changing as it repels and traps charged particles from the sun and the rest of space, protecting Earth from radiation. The sun is constantly pushing energy into space in a flow of electrically charged plasma called solar wind. That solar wind helps shape our magnetosphere, compressing it on the sun-facing side and stretching it out in a tail behind the shaded side so that it wraps around the Earth. Without that magnetic field, the Earth wouldn't exist at all, because it would be Mars. Let me explain. Billions of years ago, the red planet may have had oceans, a thicker atmosphere, and its own magnetic field. But over time, Mars lost that magnetic field. And without it, solar wind and radiation stripped the planet of its atmosphere. No atmosphere, no water. Its oceans that may have once made it habitable were gone. If Earth's core didn't produce a magnetic field, we'd be in the same boat. So Earth's magnetosphere is pretty essential. But no matter how tough our planet's bodyguard is, it's not indestructible. In some cases, solar energy can cut through the core's defenses, especially when it's really volatile. See, the sun's own magnetic field can get tangled up as it rotates, stretching and snapping, and then releasing energy in the form of solar storms. These could be massive explosions of light called solar flares, ejections of charged particles called radiation storms, or eruptions of plasma called coronal mass ejections. And these storms can cause major problems. Like in 1859, English astronomer Richard Carrington witnessed the biggest solar storm on record, a massive solar flare, followed by a series of coronal mass ejections, though he didn't know what they were at the time. The next day, the world was in chaos. Telegraph systems sparked, started fires, and wouldn't send messages. The northern lights were suddenly visible as far south as Hawaii. And they were so bright in the northeastern US, people said they could read the newspaper in the middle of the night. They thought the world was ending, and you can't really blame them. But what actually happened was a geomagnetic storm. The solar storm's particles had disturbed the Earth's magnetosphere, and that disturbance interfered with technological and electrical systems across the world. Which brings us back to our Cold War mystery. That radio outage that spooked the US? You guessed it. The culprit was really a geomagnetic storm, not an active war. Thankfully, the US Air Force's team of space weather forecasters informed the military leaders of increased solar activity before any fighter jets took off. History could have played out very differently. As for our world today, geomagnetic storms continue to happen once in a while. They can warm up the Earth's atmosphere, which increases drag on satellites, causing power outages and interrupting radio communication, GPS signals, airplanes, and spacecraft. Mass interruptions to internet connections, cell phones, and electricity can have huge consequences to just about everything that powers our modern lives. That can all feel like a lot to worry about. But the good news is, we're not doomed, even if some movies make us think we are. Like, you might have heard that the Earth's magnetic field can change over time. Its poles can shift or even completely reverse. And that's true. In the last 250 million years, Earth's magnetic poles have reversed hundreds of times. The last time they did was about 780,000 years ago, so it's probably time for another one. Movies and TV shows might have you worrying that a pole reversal would cause global destruction, leading us to a Mars-like future and a terrifying alien invasion. But magnetic pole reversal won't just happen overnight. Mathematical models suggest it could take thousands of years. And if it does, we might not even notice many changes. According to fossil records, sediment samples, and ice cores, previous magnetic field reversals haven't caused any major changes to Earth's climate or had a visible impact on life. It could affect the way migrating animals like sea turtles and birds navigate, but since that change would happen slowly, those animals would likely be able to adapt over time. The most that would happen might just be backwards compasses and confusing maps. Does that mean North Dakota would become South Dakota? So it turns out, it's kind of risky to live on a planet floating 93 million miles from a giant ball of fiery gas. But lucky for us, Earth's core provides us with the most powerful invisible armor imaginable. And while that armor can shift and change, that doesn't spell the end of the world, though it can wreak havoc from time to time. For now, space meteorologists are watching the skies for us and learning more every day. Next time, we'll learn all about minerals. See you then. Thanks for watching this episode of Crash Course Geology, which was filmed in our studio in Indianapolis, Indiana, and was made with the help of all these nice people. If you want to help keep Crash Course free for everyone, forever, you can join our community on Patreon.